Okay, well, welcome everyone. My name is Dr. Sean O'Brien. I'm one of the founding members of the League of Science Superfriends, um, in which we are a coalition of scientists, clinicians, and healthcare professionals that are interested in talking to the general public about science and sharing the latest and accurate scientific information around COVID, um, along with helping to address questions and concerns that the public may have during the pandemic, since we've been at the starting point in 2020. And so today we have the opportunity to talk a little bit today about COVID-19, around vaccines and variants and what we currently know in the field. And It's my great pleasure to welcome two panelists tonight, Dr. Julie Crudele from the University of Washington and Dr. Peter Morawski, who are both out in the Seattle area. So I want to thank them for sharing their early evening with us tonight. So just to give a little background about the League of Science Superfriends, as I've mentioned, it's a coalition of scientists, clinicians, and healthcare professionals. And we strive to try to engage the public. And we do this through our Facebook page, which is the League of Science Superfriends, through our Twitter account. We now have an email, and also our website, which our webmaster William Armerding is now up and running and hosting for us. And on the website, you can actually find web videos and webinars that we've been previously done by some of our key members. So tonight we also have Dr. Thea Golden, who's helping us run the Zoom account here, Dr. Sigrid Goma, and Dr. Letty Curry Cervantes. The three of them all participated in a webinar around COVID-19 vaccines and pregnancy 2 months ago. Sigrid recently shared a short video also about herd immunity, which is about 10 minutes long. And so look for additional web content from our team in the near future as the science continues to unfold around COVID. And so we'll have additional web content, and this also webinar will be featured at a later point in time on our website. And so just to highlight for folks that are on the Zoom call tonight, and people watching on the Facebook page, tonight's panelists are not offering any medical advice around COVID-19, and we strongly recommend that you discuss any health-related questions around vaccines and COVID-19 with your specific healthcare provider. However, we are actively trying to be a resource for questions around the latest in immunology and science related to COVID. And so tonight we've had a couple questions that we've been able to review in advance to discuss with our team tonight. And if we also ask that people that are on the Zoom to use the chat function to populate with any questions, and at opportune times we'll try to pull questions that the audience may have, either from our Facebook Live post or from the Zoom account, to have our panelists address tonight. And so without further ado, I'd like to introduce you both to Dr. Julie Crudele and Dr. Peter Morawski. I was very fortunate during my time at Penn as a graduate student to cross paths with these two talented scientists. Dr. Julie Crudele received her PhD in gene therapy and vaccines from the University of Pennsylvania.
I'm just going to correct you. It's Crudele. The Italian version is Crudele, but the Americanized version is Crudele.
Well, I've been, well, there you go. So Julie is now an acting professor, assistant professor at the University of Washington, and her research lab is focused on immune response to viral vectors. Julie, is there anything else you'd like to add about your research focus or activities with COVID?
I've just been staying up to date with all the literature and trying to be a resource to all my family and friends.
And she's been an active participant with our COVID group, and has really been terrific in terms of taking the time to address key questions around the literature, the latest in clinical trial data, and has been one of the key founding members of our COVID group way back when we started this Facebook group back in March. Dr. Peter Morawski received his PhD in immunology from the University of Pennsylvania. He's currently a staff scientist at the Benroya Institute in Seattle. And prior to joining at the Benroya, he was a NIH postdoc, where he was studying autoimmunity in mouse models. And then he transitioned out to Seattle for his postdoc there. And he's been actively characterizing memory T cell formation in human skin. And due to obviously the response to COVID by the global scientific community, his research expertise has been drawn into um, working with COVID clinical samples from COVID patients there in Seattle. And so he's actually been spending a fair amount of time actually processing clinical samples at all times of the day and night, working odd hours to really learn about what the immune response is and the types of protective immunity that we're seeing in patients that have COVID, have recovered, and also how this can inform um, vaccine development and response. He also recently completed his public policy fellowship program with the American Association of Immunologists, and actually was on the Hill last March meeting with congressional staffers uh, as the pandemic was happening. And the number one question that Peter was dealing with on the Hill at that point was, what do we have to do about COVID? What should we take this seriously or not? Um, and so he had an opportunity there. And I'll let Peter share any additional background if you'd like.
No, I think you nailed it, Sean. Thank you for that nice introduction. Yeah, I'll say that the one really interesting thing is how so many scientists that have all the tools and capacity to study the body's response to an infectious agent, who are not COVID biologists, because COVID was not a thing before this year, became COVID biologists. And I applaud all of those people. And I'm glad that I had an opportunity to take part in some piece of that scientific literature and study.
And due to the rapid collaborative nature that we've seen this past year in response to COVID, Peter's had the opportunity to work with some key labs there in Seattle, and has actually published recently on the immune response in COVID patients. And actually, one question that I've gotten, Peter, in terms of publishing around COVID is, how quickly did it take for you to get that cell paper pulled together? I know I'm putting you a little on the spot here, but this is one of this is a question I get from one of my text threads that I have about questions around COVID. And so I shared your paper last night, and one of the questions was, how much work and effort did you have to put into pulling this together, and how long did it take to actually, publish this in such a quick amount of time?
Sure. Well, certainly I think the speed with which publications are occurring is pretty rapid, given the very pressing demand to share our science and disseminate this important information as quickly as possible, not just to the public, but to other scientists. As far as really how that's possible, really the way to do that and have it be good, reliable science is you need a big team with a lot of people that are well equipped, who are willing to put in a lot of hours and who have a lot of funding, right? So you mentioned the Public Policy Fellowship program I'm part of. One of the things that we reinforced to the members of Congress was that right now, everything that's happening from the ground up at the beginning of the pandemic was being funded with whatever money was laying around. And there is really a need to increase the NIH budget, not just to support the standard array of research, but specifically COVID research. So money is a big part of it. And I'll say collaboration. There was like 25 authors on that paper, and each and every one of those people contributed something important, whether it was the actual blood draws or recruiting patients, running the experiments, being there at odd hours to grab a hold of the machines and equipment that we needed, multiple principal investigators, right? So it was just a huge collaborative effort. And so the whole paper from start to finish, right? We had a cohort of individuals that were infected in about March or April of 2020. And the paper was published in
August.
It went in September, and then it was an electronic publication, sort of ahead of print. But I think it actually made it into print on the very first day of January of 2021. But it was more or less in its final form by like September. Yeah, so it was very, very fast. But really, that was a lot of hours, a lot of money, and a lot of people, right? Which is really what something like this pandemic necessitates.
Yeah, that's great perspective. I thought it would be very informative to share with the public in general about, how much work and time that both of you have been putting in, um, to really contribute to gaining more insight in general to COVID. And so based on, some of the findings you've learned from your paper, I'm hoping we can talk a little bit tonight about what do we know about the immune response to COVID, and some of the challenges that we've seen maybe with, mild versus severe, and give you an opportunity just to showcase a little bit of what you've learned so far in terms of profiling the immune response in COVID patients.
Yeah, so thanks for that. I think one of the things that I like to highlight right off the bat is that we think of COVID as a thing that you get that has the potential to be life-threatening. And while that is absolutely the preeminent concern, I think that we get ahead of ourselves a little bit and say like, well, if you're younger, you're probably not going to die, so COVID's not a big deal. And so I did want to reinforce this notion that when you do get COVID, it is not just something that is causing old people to succumb to the disease, but this multiple system impacting disease has the capacity really to impact anyone of any age. And we see even in younger individuals who are fit athletes that have issues with their pulmonary system and their cardiac health and a number of other organ systems that have the capacity to be impacted by this systemic infection. And so we haven't, in our group, been studying the specific clinical impacts, but I just wanted to point out that those are there. This is not just a lung infection that has the capacity to put you on a ventilator, but there's a lot of other things that can happen that we're now only beginning to understand the long-term impacts of some of those. So always, I mean, what I'm reinforcing is this notion that if you can avoid getting COVID, or as we'll talk about later, the power of these vaccines to help prevent severe disease, that's really, really important. As far as what we have done, with the group that I'm part of, with the many groups that I've been part of collaborating with, we've been studying both mild and severe disease to understand really at a cellular level. I'm a cellular biologist. I care most about what is happening in our tissues, in the different cells that are in our body, to understand how we respond to all sorts of pathogens, right? Viruses, bacteria, fungus, you name it. And as Sean mentioned before, also autoimmune diseases. But in terms of COVID, we've been taking all of the tools that we have to study these different cells and tissues and trying to understand which immune cells are the most important and which immune cells are capable of protecting us from the COVID virus, the SARS-CoV-2. And so really by looking at people who have or have not been infected, people who have recovered, we call that convalescent, people who have recovered from COVID, and now in some ongoing unpublished work, people who have been vaccinated, trying to understand which of these immune cells, right, these white blood cells, how do they respond and in what capacity? And at least in the lab that I'm in my career interest, as you can see from this cartoon, there's all manner of different white blood cells scattered in amongst the red blood cells in your blood. And they each have a unique role. And a lot of people have studied many, many different immune cells that can contribute to COVID and getting rid of the COVID virus. But the sort of, I think you have a slide on this just ahead here, Sean. I can talk about the couple of cell types that we are best equipped to study in the group that I'm a part of. And maybe you've heard something about these more recently. I think a lot of people have been conditioned now to know about like antibodies, right? Is like a word that's on the tip of everyone's tongue, and B cells and T cells. And so if unless you have any other questions, Sean, I think maybe I'll just jump in and talk a little bit about some of these cells.
Absolutely.
Is that all right?
Yeah, go ahead.
Yeah, so we have been working with Marion Pepper's group and a number of other groups here in Seattle, as well as across the country. And right, everyone's talking about antibodies right now. Antibodies, what happens with variants in antibodies? Julie and I will talk about that a little bit later. But just by way of sort of an introduction, right, we have these B cells. They're called B cells because, well, there's a whole history, but they live in the bone marrow, and then they can go around our whole body through the lymph, through the blood. And one of the groups of these B cells has this really important function to create antibodies. And some subset of these antibodies, as Julie will describe in a minute, has this really wonderful capacity to inhibit or neutralize, or in sort of just more simple terms, just slow down or stop a virus, any virus. And in this case, in response to infection or in response to vaccination, our body does this really wonderful job of creating these antibodies from these B cells to slow down the virus. And then the other sort of main arm of this very specific piece of our immune system, of our white blood cells, are these T cells. In the middle, there are these green cartoon helper T cells, which really, I just put them there to show that they help with B cells essentially to create this antibody response. So they're quite important. And then we also have a group of these cells called killer T cells. And what their job is to do is simply find cells in our body, tissues in our body that are infected with a virus, and try to eliminate those infected cells that are part of tissues to try to clear that virus. So that's really just the most basic upper layer of the immune system as it functions, this hyper-specific set of cells that can find a virus. There's a whole manner of ways in which it does this, and this just sort of highlights some of the ones that we've been looking at and classifying how these cells in their percentages and in their function are different before and after infection and before and after vaccination.
And I think one other thing we'll highlight too is that in the immune response, we also have the generation of memory cells. So in response to an infection, we'll start to get memory B cells and memory T cells, which help to prime the immune response against active infection in the future. And that's one thing that vaccines really do so well, and help you avoid some of the deleterious side effects that we see with infection in general, where the vaccines can help you prime and generate these B cells and T cells that provide protection, and do so with very high levels of robust activity in the future. But as you've mentioned, Peter, we hear about antibodies in the news, and myself as an immunologist, who it's one of the craziest things about being an immunologist right now is just having immunology being in the mainstream news on a daily basis. So it just always blows my mind now to hear about antibodies and T cells being reported in the general newspaper or on TV all the time. It's an amazing time, and I don't know if I've ever experienced anything like that. And so, in terms of looking at these antibodies, we hear about this all the time. And so, Julie is going to talk a little bit more about some of the questions about the quality of the antibodies here. And so I think one of the questions that we have is, we hear about in the news about antibodies, can they bind the variants? Can they, are they, do we have loss of antibody function? Do variants escape, from the antibodies? So I think it's important to also keep in context the type and quality of antibodies that are generated, and also the functional activity of antibodies. And so this is one area that Julie's been actively thinking about. And so I'd like to give us this opportunity to describe a little bit more about antibodies and discuss a bit more.
Yeah, I think it's really important to understand what antibodies do when we start talking about variants. So the news articles that most people hear about really are focusing on neutralizing antibodies, which in this image that I have are the two bottom sections. So neutralizing antibodies specifically is going to bind the spike protein in such a way to directly block the ability of the virus to get into your cell. So it's going to either inhibit the ability of the virus to bind with the receptor, or either like directly or sterically. And these are very important, obviously. These are what can totally block the ability of the virus to infect you. But equally important and talked about a lot less are binding antibodies. And binding antibodies help to clear the virus out of your system. So they can do that two ways. They can either mark the virus for destruction by white blood cells, or they can just aggregate the virus so that the virus can't get into your cells. And both of these things protect you. Now, only neutralizing antibodies can you measure those effects in the lab. You can't measure the effect of binding antibodies. You can measure whether they're there, but you can't measure the impact of them outside of the body because they rely on the existence of white blood cells. And so when you hear news articles talking about loss of neutralizing antibodies because of variants, you need to keep in mind that that's only one kind of antibody, and the other kind is equally important. And if you move to the next slide, I can give you an example. So this is, just a cartoon of an example of how variants may impact antibodies. So on the left, you have a representation of the original spike protein and how you may have a bunch of different antibodies binding to it in a bunch of different places. And maybe that antibody right at the top that Sean was just, or Thea, I don't know who's controlling it, was just circling one at the very top. Maybe that's a neutralizing antibody because that blocks the ability of the spike to bind to the receptor, and so it blocks the entry into the cell. But all those other antibodies are marking the virus to be destroyed, and so they're both important. And then let's say over on the right, you have a variant that has 3 mutations shown in yellow, and the top one and the one on the right, maybe they completely eliminate the ability of those antibodies to bind to the spike protein. And maybe the one on the left just lowers how tightly the antibody binds to the spike protein. As you can see, there are still a bunch of other antibodies binding to the spike protein. And so if you have enough antibodies, you can take a few hits and your immune system is still going to work to protect you. So if you move to the next slide, this is just a made up graphical representation of what that might look like. So in the green section would be where you are completely protected. Your antibody level is high enough that you can be exposed to SARS-CoV-2 and you're not going to get ill. Maybe the yellow one, or maybe the green is actually you don't even get infected. And then the yellow section is you get infected, but it's really a mild infection. You have a runny nose, sort of like a typical cold, but you don't end up in the hospital and you don't end up dead. And then in the red section would be where you get a full-blown COVID infection. So the idea here is that you want your antibody level to be as high as possible. And so people who have been naturally infected or partially vaccinated, they're going to have antibody levels that are protective. Fully vaccinated people are going to have even higher levels of antibodies that are protective. So then as you move across that graph, perhaps this represents time. Your antibodies can wane a little bit over time, but if you start out high enough, it doesn't really matter. You never get down into the red. The other thing that the x-axis could represent is a accrual of mutations. So maybe number 1 is a variant, and number 2 is a further mutated variant, and number 3 is an even further mutated variant. And so with each variation of the virus, your antibody level drops a little, not the ability of your antibodies to find that virus drops a little. But again, if you're starting out fully vaccinated, you have so much cushion with your high antibody levels that your antibodies can still handle a variant. Because as we saw on that last slide, you still have a bunch of antibodies binding the virus. So this is, again, it's just a theoretical graph, but it's a representation of why being fully vaccinated really can protect you over time and across variants.
Julie, do you mind if I add one quick thing to the end of that?
For it.
So I think that the antibodies are absolutely important. There's plenty of evidence from other studies, like with polio, where antibodies are absolutely the thing that's most important to keep you protected. And one thing that I think gets lost in some of the knee-jerk reactions to headlines is that antibodies are going down in response to a variant, and that means we're all doomed, right? And the nice additional buffer on top of this nice demonstration that Julie gave is also that we have those other cells that I talked about on the previous slide, those T cells, right? And those T cells, especially some of those helper and killer T cells, we're not accounting for those in studies that just look at antibody. And so even when antibody does go down, you still have this additional layer of protection in these T cells, and it's often not talked about. And so there's even more cushion than people realize in terms of how robust our immune system is to help after it responds to one of these vaccines, for example, to really protect us. And I just wanted to drive that home, that I think a lot of people see some really scary doom and gloom headline that, you know, this variant is having a reduced amount of antibody and we're all doomed. And we still have, as Julie pointed out, probably more antibody than we need in some of those cases if we've been fully immunized. But we also have these T cells, and that's what we've been studying. And they do a really, really nice job to protect us against the virus. And on top of that, some of these T cells and some of these B cells are not even seeing the same piece of the virus. So they're non-redundant, which is really important because we have multiple levels of protection. And I love driving that home because it's a hopeful message in the face of some doom and gloom headlines in the papers. Is that fair, Julie?
It's fair. And also to add on to that, so a B cell that has already been exposed turns into a memory B cell, and those respond so much faster to a new version. So you're better off in every level. I agree.
And I think it's also important to highlight that we have crosstalk between T cells and B cells too. So they interact, and so they help drive diversity in the T cell response. And that helps provide a generation of newer antibodies that also can have better binding affinity or neutralizing activity to the COVID variants also. So I think it's something we have to appreciate is how diverse our immune response is. And so, you know, the key takeaway, like we've mentioned here, is that when you see in the news that, you know, loss of neutralizing activity or a reduction in neutralizing activity, what does that mean? You know, Peter and Julie have both highlighted the key point that you still have a whole other compartment of your immune system that can actively go against COVID here. I had two questions actually. That, you know, Julie highlighted a good point about, you know, in the news currently, we talk about neutralizing antibodies and that we can't really detect binding antibodies. You know, one question.
So we can detect them, we can measure them, but we don't know what we don't know the correlate of protection with them.
Right. So, you know, one question I received recently was, what about T cells? What about these antigen-specific T cells? Is there an easy and quick way to test for these antigen-specific T cells in the same way that we can, you know, look for the neutralizing antibodies in patients? And my thought was, you know, I'll throw this out to both of you, because from what I'm aware, there's nothing commercially available that we can quickly do a test for COVID-specific T cells.
There is a commercially available test. It's called T-Detect.
Okay. What's the? I'm not familiar with that. So what's the breakdown on that, and how easy is it to get commercially?
It's very easy to get commercially. You need a prescription, although I believe the company offers a doctor to give you the prescription.
Okay.
And then it's just a simple blood draw.
No, that's great to know, because that's something I was unaware of, and I was under the assumption it would be more challenging to get to determine that. And the second question that I've typically received is, and I'm sure you've heard this one before also, is that, you know, a lot of people feel that maybe they had COVID back in, you know, January 2020. You know, so one question is, you know, maybe they had it and resolved it. If they decide to get a test for their neutralizing antibody titer or antibody titer in general now, a year out after a potential infection, would there be a chance of even being able to detect whether they had antibodies to COVID? Or because your immune system is probably not active, the levels might be too low?
So it really varies. It kind of depends. It often depends on how ill the person was. If you had a very mild infection, which means that you were not hospitalized, those antibody levels can drop pretty fast in some people. Hospitalized patients tend to have more robust immune responses, so they tend to have higher levels of antibodies. But even if you've been vaccinated, or even if you've been infected, as this theoretical graph shows, you benefit from getting vaccinated, and it will very likely increase the length of time that you are protected, and also how protected you are against variants, because we know there are outbreaks happening, like in Manaus, Brazil, where 70 to 80% of the population there was infected in a first wave, and they are having another outbreak where, much like India, they're running out of oxygen, the hospitals are overrun because people are being reinfected.
That's a great perspective, Julie. And I think that segues very well now to, what do we know about vaccines and variants?
Sean, if I might add to that really quickly.
Oh, sure,
We've
yeah.
actually been studying this. So when we published our study in Cell, we were looking at people's antibody response after infection. This is before the vaccines existed available to the public, and they were only being sort of tested in clinical situations in these trials. And we looked originally 1 to 3 months after infection at antibody levels in mildly infected people, and we saw a pretty robust response. And then Shane Crude's group and a number of others followed up and showed that that antibody level does persist to like 6 to 8 months. And now in some unpublished work, we're seeing that the levels do decline like this cartoon shows, but you can still find, even in mildly infected people, some antibody levels that persist up to a year after infection. So you'll find them, right? You'll find them. But Julie used a phrase before, which is pretty popular in epidemiology and virology, correlates of protection. And really, that's just a fancy way of saying what is actually the important bit, right? And we know that antibodies are super important, but we also know that people who were previously infected can get reinfected. So I know you were about to transition into this, so I'll toss you a softball here. What it really comes down to is we want to be able to give ourselves the best possible chances to deal with reinfections such that we don't get reinfected at all, or so if there is a reinfection, we have a really cool special case that we'll talk about later on. It is really mild or almost completely undetectable, right? And it really seems like the vaccines are just doing a remarkably good job at protecting us in that manner. And so maybe that's a good way to kick it forward.
Yeah, that's an excellent point about being previously infected with COVID and what your chances are with the variants. And so we'll shift over to what we know about the current variants. And Peter, I'll let you and Julie discuss detail a bit more about that. And I think also, obviously the main concern that the buzz has been, dating back to last summer about, the UK variant or the different variants that seem to arise. Everyone seems to be worried that the vaccines will be ineffective and completely done for. So Peter's pulled together this nice table about the vaccines and their efficacy against the different known variants. And I'll pause and let him walk us through this.
Yeah, and I probably won't really. I'm not going to walk us through it because this is just it's a lot, right? And I think that this is being recorded. People can go back and take a look at this. This is actually a slide that I made based on something that was presented by Tony Fauci recently at the AAI meeting that Sean referred to, the American Association of Immunologists. We had our annual meeting. And really what this is just meant to show you is some things that you have probably seen in the news media coverage of COVID-19 or these variants, and you'll recognize a number of them, right? This UK originally discovered variant, which we call B117, or this South African originally discovered variant. I'll point out that these were originally found in those places, but we don't really have a sense of where they came first. There's, a very good chance that some of these may have arisen in other places. They were just detected first in a country that tests more, for example. I'll just leave it at that. Or this Brazil variant we call P1. The basic thing that I want to get across here is that at all of these red bullets, the clinical data that is available, the real world data that is available, both from the clinical trials and also from just follow-up studies of people in a population that have been vaccinated, what we see again and again and again is that these variants show up and vaccinated individuals may have a reduction in their antibody levels. And as Julie pointed out, how much of a reduction is really clinically significant and how much is needed to protect us? That's sort of an open question. But again and again and again, what you see here is, right, likely covered well by, moderately to severe reduced vaccine efficacy. However, symptomatic disease very low, or hospitalization low, or death low. So there's all these variants. They are called variants of concern because we need to be looking into them. We need to be thinking about how the virus is trying to improve its fitness, improve its ability, because this is just the way that viruses evolve, right? They try to make themselves better. But as far as we can tell, we have tons of reassuring data now showing us that these vaccines work really well, and not just against the original, what we call parent strain of the virus, but it really gives good protection against severe disease, hospitalization, and death for all of the variants that we've encountered so far. And the new ones that are coming out, some of the mutations in India and places like this, we are doing our best to look at those, and that's why they're called variants of concern. We're going to keep our eyes closely on them. But for the time being, what we do know is that people who are going into the hospital these days, particularly in this country, they are largely unvaccinated people. These vaccines, the three of them that we have these emergency use authorizations for in this country, the Pfizer, the Moderna, and the J&J, gosh, they do a really good job at protecting us from these variants and from the virus in general. It's very, very reassuring data. Oh, right. And so I threw this in here. I think this is maybe a little data heavy, but on the bottom are written some of those variants that were referred to on the previous slide. And really what this is meant to show is that those neutralizing antibodies, the ones that you can measure the efficacy of in the circulation, in the blood or the plasma, when you get that first dose of a Pfizer, and boy, does that second dose just absolutely put you over the top in terms of just a huge amount of neutralizing antibody. This is a slide adapted also from Tony Fauci's lecture, taken from this Nature Medicine paper recently in 2021. And this is not the only study that shows this. There's tons of studies that show it, more data than back in here. And this doesn't account for the Johnson & Johnson vaccine, which is only a single dose, but does a wonderful job at creating these neutralizing antibodies as well that protect us. And on top of this, none of this says anything about the T cells again, because everyone's so antibody crazy. But we are now looking at the T cell responses, those virus-specific white blood cells that can actually kill and eliminate virus, really, really nicely induced and boosted by that second dose of the Pfizer and Moderna vaccines as well. It's really quite remarkable.
Okay, thank you for that overview, Peter. And I think, for kind of to wrap up our last segment here, we're going to talk a little bit more about, where we are in terms of vaccines and where we go from here in terms of what does it mean to be with a group that's been vaccinated, and how's it, and what do we know about how remarkably well these vaccines are working. And so, there's been some, discussions in general about outbreaks amongst vaccinated people, and mentioned in the news, references to breakthrough infections, and different news stories have been highlighted. And with this being baseball season, it's kind of fitting that we actually have a situation in which Major League Baseball teams are under the microscope for their vaccine. And the New York Yankees actually had this COVID outbreak, as New York Times likes to highlight it. But I think we sometimes have to parse the news, the stories here a little better. Talk a little bit more about what do we know about this example here, and what can we learn from it.
So I was really excited about this news. I think this news is fantastic news. So before I talk about the Yankees, I want to remind everyone of a story that happened about a year ago in Washington. There was a choir group that met before they realized how bad things were. They were obviously unmasked, and there were about 61 people who attended this choir practice in Washington, and there were 52 cases off of one choir practice from one single infected person showing up. So the attack rate, or the number of people that got infected from this single infectious person was 87%. Compare that to the Yankees. So the Yankees, as a group, there are about 50 people that travel together, coaches, players, and staff. They are more than 85% vaccinated. We don't know the exact number, but we know they've hit that threshold, because when you hit that threshold, the Major League Baseball says that you no longer have to wear masks or physical distance as a group. And so they were following all the guidelines. They were probably mostly not wearing masks, not physically distancing. And there was a rain delay, which led to all the coaches and staff gathered in a small indoor space for an extended period of time. And it turns out that one of the coaches was infected. The coach that was vaccinated, but he was also symptomatic. And so in the next 5 days, 8 people tested positive. And then about a week later, one other person tested positive. And the positive tests have stopped. They haven't had any positives in the last 12 days, I think. So in the end, 3 coaches, 5 staffers, and 1 player tested positive. 8 of the 9 were vaccinated. I'm not sure that the most recent positive person was vaccinated. But importantly, 7 of the 8 vaccinated people were asymptomatic. So the news was fantastic. Only 9 people were infected, and only 1 person that was vaccinated had any symptoms. Those symptoms were very mild and short-lived. So this ended up being an attack rate of less than 20%, as compared to that choir practice where it was 87%. And so basically, the efficacy of the vaccine was pretty much exactly what they had seen in the clinical trial. And not only that, but the people who did ultimately test positive, 7 of the 8 vaccinated individuals had no symptoms at all. The only reason we knew that they were positive was because the team gets tested all the time. So these vaccines are doing exactly what they're supposed to do. They prevented the vast majority of the infections that you would have expected. The people that did get infected were not sick at all, or they had a small cold, and the outbreak ended very fast and didn't spread really beyond the team. So basically, it's the best case scenario.
So Julie, you mentioned this is a great development then, and I mean some of the key takeaways here that we're pretty much at a point where if you're vaccinated, your prevention of severe COVID, and it really controls the reduction in disease transmission here. I mean, that's some of the key takeaways we're seeing with this case, right?
Yes, and so someone popped up with a question: how safe is it to be indoors with other people when you're vaccinated, but you don't know when other people are vaccinated? That's basically this scenario, right? There were some people that probably were not vaccinated. Well, we know that at least one person wasn't. We don't know how many of the team was unvaccinated. It was some number less than 15%. But the vaccinated people, no one got severely ill, and the vast majority of them didn't even get infected. So as long as you are vaccinated, fully vaccinated, and as long as you don't have a particularly severe immunodeficiency, you can feel very safe following the CDC guidelines, which is why the CDC made the guidelines what they are. So and basically, this is how we get out of this, right? Vaccines are how we get out of this, because we will all be the Yankees team. And it just wasn't devastating for them. It was barely a blip.
Well, that's a great example of where this future might be and how we move forward, and how fortunate we are to have this level of vaccines, very effective vaccines, especially in the country too, at this point in time. So in the remaining 10 minutes here, so I just wanted to open it up for any additional questions or thoughts that Peter and Julie may have around this, and I'll stop the screen sharing as or I can leave it on this slide at this point in time. But maybe I'll just open it up for any additional questions that we may have from the audience or from the Facebook page here. And did I lose Julie? Nobody hear me either?
We can hear you, Sean.
Okay, great. And are there any other questions we might have in the chat? I don't see anything on the Facebook right now. But no, I think it's a great example of what we're seeing here with the Yankees, is that we know that now that if you're vaccinated, you're going to have great, robust, long-term immunity. There was actually reports today coming out about that we're seeing up to potentially, I think, a year now with protective immunity. Peter's actively characterizing the memory T cell response in patients, and also how that'll help inform vaccines in general. And so I think we're really getting to a better point where, the key takeaway, I think, from our presentation today is that vaccines are really the way to move forward and help us restore a new normal. So if there's no additional questions or comments, I'll let Peter and Julie provide any closing remarks, and then we can wrap up. I can't see the questions here. Is it in the chat?
So there is one in the Zoom chat right now, Sean.
Okay.
Oh, sorry, I can chime in. My question was just about booster shots. Can you tell us a little more high level about kind of what they are, when they're needed, when they're not, and how that works with the specific vaccine mechanism? And this is coming from a non-scientist, obviously.
Can you hear me okay? I don't know if it's my internet connection that's unstable or if it's the host. Okay, I can certainly, I will.
What I'll do is stop sharing.
All right, should I try again? Can you hear me?
We can hear you.
Yeah, go ahead, Peter.
Okay. Yeah, so boosters are a wide open question right now. There is certainly the possibility that they will be needed at some time. It's really unclear what that will be or when it will be. There is an equally good argument to be made that we will need booster doses at some point in the future. And there's another equally good argument to be made that these vaccines are going to work really well, and the virus that causes COVID is going to become something that is with us more or less permanently, and we get potentially reinfected in the way that the Yankees did every few years. It's kind of like one of these common cold viruses, and you get a little booster, and that is what gives you your jump in your immune response. It's hard to say. I think there's epidemiologists that are tracking this. There are clinicians that are studying this. What I know is that the pharmaceutical companies and the scientists that work there and who are collaborating with them are tracking these variants. They're tracking ways that we could have a third dose or a second dose in the case of J&J, these booster shots, to help improve the immune response to some of these variants. But I think that right now, the main goal is to get people vaccinated in the first place, and that our focus should be on that first wave of vaccination. We have about 62% of people in the country that have been that have received, I believe, at least one dose, and about 50% that have been fully vaccinated. And as those numbers continue to climb, I think we're going to learn a lot about how good these vaccines really are at protecting us. And then we'll track long-term studies of reinfection, and that sort of public health data, that epidemiologic data tracking how people get sick and what is happening with vaccinated people, that will tell us whether or not we need to engage with, initiate some of these, second or third doses, these boosters. So people are working on it, they're tracking it, it's important, but imminently, I think people who have been vaccinated, the data shows us that as far as we know, these vaccines work really well, and we should feel sort of relieved in that sense. But at the same time, we are hedging our bets, and people are studying these things and preparing for the potential for boosters if that necessity comes.
And Julie, we had a question about about whether boosters may be necessary in the future or not.
I can't hear you, but I'm assuming you're asking about the question in Facebook. I commented, I don't know if you guys saw that. So did you address the fact that the clinical trials are still going on?
Not yet.
Okay, so the clinical trials are 2-year clinical trials.
We were discussing a question in the Zoom chat right now on the need for boosters. But yes, we do need to get to that Facebook question as well.
Okay, so I can't see the Zoom chat because every time you get kicked off Zoom, it erases the chat.
Okay.
So I'm gonna assume that Peter already covered this, since I know he and I think the same way, which is I suspect that once it will be enough, but we're ready to go if it's not. And then to address the Facebook question, how will we know that the vaccines are losing efficacy if the CDC is no longer tracking mild infections? Feel like we're losing things everywhere. Okay, I'm gonna assume that you guys can hear me until someone waves at me. So the clinical trials are 2-year clinical trials, and we're only about 10 months into the phase 3 2-year clinical trial. And so the companies are going to continue to monitor for infections in the people in the clinical trials. And at the end of 2 years, if the vaccines are still very efficacious, it's what usually happens, and I would be really surprised if it doesn't happen here, is the companies will start what they call a rollover trial, where they maybe don't take all 30,000 people, but they take a portion of the vaccinated people and they roll them into a longer clinical trial where they continue to do blood tests and monitor for infections and antibody levels and those sorts of things. So the companies are a major source of surveillance to make sure that the vaccines stay efficacious. And then also, we're not going to go from complete protection and mild infection to hospitalized and dead, right? It's going to be like that curve showed. It'll be a slow change over time. And so if for some reason the companies don't notice that their vaccine efficacy is waning, what we'll start to see are moderate infections, right? So it's more than a cold. You end up at the doctor's office and they test you. And so those will be the signs before we end up in another major death outbreak. So we'll have lots of warning if the vaccine efficacy is waning.
Great. Well, thank you, Julie. Can people hear me? Okay, good. I suspect we have. I'm going to blame it on the thunderstorm that's outside right now. I think that's what's killing everything here. So, but I'd like to wrap it up and thank Peter and Julie a great deal for taking the amount of time out of their very busy work schedules to help address questions from the public and put together this seminar. It's been a great pleasure to have you both participate in our webinar here. And I want to thank you again. And additionally, if there are other questions or comments, feel free to use our email at sciencessuperfriends@gmail.com or find us on the Facebook page, the League of Science Superfriends. And Peter and Julie are happy to address additional questions that come in through those points of contact. So I'd like to thank them again profusely for their participation tonight. And hopefully this was helpful. We look forward to addressing future topics that come up that may help the public as we navigate getting out of the pandemic. And thank you again to the team tonight that helped put this together. All right, everyone have a good night, and we'll take care and talk soon.
Thanks, everyone.